Good morning, students. Can you hear me?
Yes.
Okay. So let's start the class today. We start with the revision. Okay. So in yesterday's class, we looked into the overview of Asic design flow. So first we started with some basic concepts related to integrated circuits, something related to photolithography, and how the chips are fabricated, and then we looked into difference between a silicon ingot, wafer, die, and chip. Right. We also understood the concept of yield and what are the figures of merit in an integrated circuit. Then we looked into the basic design flow or design implementation flow. So in this, we said that we divide it into two major parts. One is logic synthesis, and the second part uh, is the physical design, right? So we saw that logic synthesis basically converts an RTL. It takes an RTL and converts it into a netlist, right? It gives you a netlist, and we saw how a netlist is represented. And then we saw that physical design basically takes the netlist and it creates the layout. It creates the layout. And this layout finally goes to the foundry, and this is basically fabricated in the mass in a large scale, right? So this is the top level view. Then we saw that physical design is basically, it consists of many steps. For example, chip planning. Then we saw that after chip planning we do placement of the standard cells, and then we do clock tree synthesis, which is known as CTS, right? So in which we route the clock signals from the clock generator to each of the flip-flops. And then for the after CTS, we do routing, which is again divided into global routing and detailed routing. And once we have done the detailed routing, our layout is complete. And then we do some sign-off checks. And if some changes are required, we do through ECO, and then we tape out the chip, right? And then it goes to the foundry for fabrication. Then we saw that this is the implementation flow, and then verification is also important, and it is done throughout the flow. And we saw what are a few types of verification. And then we saw that when the chip is fabricated, then some of them chip can actually be having defect or faults, and we need to basically detect those faulty chips, and then stop it from reaching the end user, right? So that is very important. So to do that, we do a wafer level testing. We apply test pattern and see the output. And to allow these all things to happen and to make the test efficient, we do something which is known as design for test. We make some changes in our design, and and DFT or design for test are some of the steps, or is a kind of group of steps that needs to be carried out during the designing that helps in testing. Okay, so these things were discussed in the yesterday's class. So if you have any doubt, please ask now. So if you have any doubt regarding yesterday's class, please ask now. This is an opportunity for you to ask questions. Okay, so am I audible?
Yes, sir. Yes, sir.
Okay, so I hope everything is clear. Okay. So, how many of you actually know Verilog? Let me understand, or have you designed earlier in Verilog? So let me, uh, I will have some idea that how much I need to discuss Verilog in this class, because today's lecture will be having on simulation and synthesis using Verilog, right? So, how many of you don't know actually? Can you write in the chat box that I don't know? So I'll have some idea regarding that, or if you know, you can write there also. So please do that in the chat box, right? So I don't see any message from the students or the participants. So you can write in the chat box whether you know or don't know. Very long. You want me to discuss very long or not? So when you are saying no, what do you mean by I don't know very long, or you don't want me to not discuss very long? What do you want? So please be a little more clear. So I see only one student has written that he very low his nose, right? So and only one student is writing I know, right? Two has written I don't know, right? But from that I cannot assume much about or cannot guess that what. So I will discuss maybe a little bit on Verilog, okay, before going to the simulation and synthesis. Okay, so three students wants me to discuss. Okay. Okay, so I give 1 more minute. If anyone wants to write something, please write on the chat box. I am reading. Or you can talk to me also if you want to. So others are not writing anything. I guess so. Are you even listening to my lecture? I'm not sure. So let me call a few names from the participant. Chaya, do you know Verilog?
Hello.
Yes.
Sir, I'm not familiar with Verilog.
Okay, so please write that in the chat box that you are not familiar. Okay. It
Okay.
is not. It is not a problem that you don't know, right?
Sir, actually, I joined right now just, so
Okay.
I don't know about it.
Okay, no problem.
Yeah.
So please write whether you know or don't know. Okay.
Okay, sir.
I want to see or actually see if I discuss advanced concept and you don't know very long, it will the discussion will be of not much use, right? So please write. Medha Bhaskar, do you know?
Hello? Yes, sir. I know
You
very
know
long.
you know very long.
Yes, yes, yes.
Okay, so please write on the chat box. Why don't you write? Ravi Prakash, you have written, right? Okay. Srinidhi, do you know Verilog?
Sir, we've learned the basics, sir. So I'm like, I know a little bit, but not like very fluent in it.
Okay. Okay. So please write that in the chat box, whatever you feel like. Please interact in the class, right? Then only you will be able to learn better. Ashmar,
Yes, I'm familiarized with the basics of Verilog, like creating Moore and Mealy machines, mux adders, etc.
okay, good. Okay, so let me start. Give a very brief account of. I'll go very. I will describe some concepts of Verilog. Okay, and move rather fast because I think at least you are exposed to Verilog. Okay, so let me go quickly over it. So we have seen that the synthesis, what do we give? We give RTL, the library, and the constraints. Okay, so the RTL is in the form of we give it in a Verilog file or VHDL file or a mixed file, right? And then the library in .lib file, and the constraint in the SDC file. So these library and constraints we'll see in tomorrow's class. Today we are concentrating on this RTL, the Verilog file, right? And how the synthesis of RTL file is done and how the simulation is done, some basic concepts related to that. Okay, so now what is an RTL? RTL is model, or how is RTL model? RTL is model or written using hardware description language HDL, and two common SDLs are Verilog and VSDL. Okay, now what is actually distinct or what is special about hardware description language? Can someone tell me? How is it different from other programming language?
So the parallelism is provided in HDL.
Okay, good. So that is one of the most important differences. Okay, now let me give some brief account of this history about this VSDL and Verilog. So VSDL was started initially as a documenting language for integrated circuits in early 1980s, and then it was standardized in 1987 for modeling of the circuits, right, rather than documenting, modeling, and for simulation, right. On the other hand, Verilog was actually started for simulation. Okay, so the Verilog is a combination of two words, verification and logic, and it was started for right from the beginning for the purpose of verification, and that is simulation based verification. And therefore the syntax and semantics of the Verilog language is very much easy, or the more meant towards doing fast simulation. Okay, so that is what has happened, and VSDL was more documenting, and that's why it was more elaborate kind of language rather than was more suitable for simulation. Okay, now after in around 2005 or so, so what happened is that a system Verilog was created, which is a superset of Verilog plus additional features. So can you switch off your mic, please? Vishal, can you switch off your mic, please? Vishal Kumar Gupta. Vishal Kumar Gupta, can you hear me? Vishal Kumar Gupta, can you hear me? Okay, so system Verilog is a kind of Vishal Kumar Gupta. I don't know. Okay, so let's continue. So in around 2000 time frame, the system Verilog was standardized, and it contains much more features for verification. Okay, not only using simulation but also using assertions, and it has coverage model, and it is much richer than Verilog. Okay, and Verilog was basically having more of syntax of C language, and this system Verilog actually had classes and other things, and it adopted features from C++, right? It is more object-oriented programming in system Verilog than in Verilog. Okay. So now, what are the distinct features of hardware description language? And the most important is, of course, the concurrency, right? So, so concurrency means that in hardware, computation can be done in parallel. And for example, if you SDL syntax should and semantics should be able to distinguish between two kind of operation, right? It is the parallel and the sequential operation, right? For example, in this circuit, suppose this is your circuit, then this will work as a in a parallel manner. If you apply A, B here signal, X will change irrespective of what is happening in C and D, right? And if you apply C and D, any change, the Y will change irrespective of the other part. These two components are basically working in parallel, right? These two components are working in parallel. Now, instead of this hardware, if you consider that I am writing something in a programming language, X is equal to A plus B, Y is equal to C star D, then this kind of thing will be in the procedure in the programming language, which doesn't support concurrency. It will be actually executed sequentially. That is, this instruction gets instructed, is executed first, and then C star D, this one is executed next. Okay, so this is how the execution of the statements will occur or will be done in a traditional programming language. It will be done in a sequential manner. But in hardware, what we need, how does a hardware operate? It operates in parallel. It can operate in parallel, right? So if it can operate in parallel, then the language should support features where you can specify that this is my parallel operation and this is my sequential operation, and so on. And that is these features are basically supported inside the in Verilog, right? The other is a notion of time. You describe behavior of a circuit with respect to time, and you can distinguish between concurrent and sequential operation. This has also got or this is also related to time, right? Concurrent and sequential operation. And then you can apply you should have the ability to create a waveform and representation of finite state machines. So these kind of things can be done in representation of finite state machine, can be done in traditional programming languages also, right? But the features in the hardware description languages are much richer to represent finite state machines and so, right? So then there are some more characteristics or distinct features for SDL. For example, you can have something known as something like the strength of the signal, right? For example, you can have a multiple driver, and depending on the strength of this and this driver, the value of Z will be taken. For example, if it is a weak low, weak zero, and it is a strong one, right? Then the output will be a kind of strong one, right? So this is kind of the strength of the driver that needs to be specified, or that can be specified in an SDL, and in traditional programming languages these kind of features are not available. Then you can specify edges of the clock, and this is important for modeling of sequential circuits. And then you can have bit, or the SDL have features to do operation on bits and a group of bits, right? For example, you want to take a third to 10th bit of a signal and then do something, then you can easily write the statements based on the bit select and part select of a signal, right? So these features are available in SDL, and are not that much rich or not supported in traditional programming languages. Okay. Any questions from what we have discussed so far?
So what is tri-state?
Tri-state is that you can have 3 states for a signal, right? So as the word means, tri-state, you can say have three states. So what are the 3 states? So usually if you have a bit, by a definition, bit can take 2 values, right? But bit is basically binary digit, and binary can take 2 values, 0 and 1, right? But in a tri-state, the third state is the high impedance. Okay, high impedance, meaning that the output, the value at the output is not known, right? And the driver is at the high impedance, meaning that if you have, suppose you have a buffer, right? And if you have 0 here, then you will have 0 here. If you have 1 here, then you have 1 here, right? Now, if you have this as a tri-state, what it means that the input and the output, these are isolated, or there is a higher there is a high impedance between the input and output, and you can consider it as an open circuit. Okay, so high impedance means high resistance, a kind of thing, right? You have the current will not be able to flow, right? And therefore you can consider it as an open circuit, right? So the third state is an open circuit. Now where are these things used? So you can have a kind of tri-state buffer, right? You can have you have a circuit element which is known as tri-state buffer, in which you have input, you have output, input and output, and you also have an enable signal. Okay, you have an enable signal. So whenever the enable is 1, then input goes to the output. Whenever enable is equal to 0, then the output value becomes the tri-state, which we denote by Z. Okay, the output becomes Z or tri-state. Now, how do you use? So again, someone has Umar Imtiaz. Okay, so
Sir,
yes.
I have one doubt in the tri-state. What I understand, correct me if I'm wrong. It is just wire is opened, like output is not connected to the circuitry. Is that the tri-state? I mean, high impedance state.
You can consider like that. Okay, so a high impedance literally means you have between the input and output, you can consider the resistance is very high, right? Or the impedance is very high. And in the ideal case, that is an open circuit.
Okay, sir.
Right?
Thank you.
So from your understanding perspective, from the functionality perspective, your understanding is fine. You can consider it as an open circuit, right?
Okay.
But if you consider at the circuit level, then there is not some. It may not be actually an infinite impedance. There may be it will be high impedance, may not be infinite, right? So this is the ideal. In an ideal case, then open circuit is an impedance of infinity, right? But that is an ideal case, right? In a real circuit, it will be very high, but it not be infinity. Okay. So now where is this tri-state used? So the tri-state is used, for example, if you have a bus and or a net and you are having multiple drivers, right? So the signal will be coming from all these places, all the inputs, right? And then you join the output. You join the output and it goes to somewhere, right? So now you will have enable signals. You have enable signal everywhere, right? Now, where you have to ensure in your design that only one enable is one. Okay, all others are zero. All enables are zero. So when all other enables are zero, these are open circuit, and the one which is actually enabled, the value of here will come. If it's zero, you'll have zero. If it is one, you will have one, right? The others, even if it is zero or one, it doesn't matter because the enable is zero, right? So, but in a tri-state circuit, you have to ensure as a designer that only one of the tri-state is on. If multiple tri-state gets on, then again the problem can be of a short circuit, right? Suppose you have an inverter, a CMOS inverter, okay, and you have another CMOS inverter, and you have connected the output. What will happen? What can happen? Any answer? It is not a tri-state, it is simple inverter. What can happen?
So what's the question?
The question is that you have an inverter. You have this inverter, you have another inverter, right? Now you connected the output of one inverter to the output of another, like this, what I have done. What problem can happen in this circuit?
In real time, whatever the signal strength is more, that will dominate.
I am talking about CMOS circuit, okay? But please understand, okay? So in CMOS circuit, you will always have a strong zero, strong one. You cannot have a weak zero or weak one, right? In a CMOS circuit. Why? Because in a CMOS circuit, the output is always connected either to VDD or ground through some low resistance path, right? It has to be there or at all instant of time in a static condition, right? So what can be problem in this configuration?
Sir, in real time, it is like a VDD shorted. VDD and ground are connected, like that scenario it is.
So when can that happen, and why these two will be connected together at the circuit level? So you are correct in the sense that suppose this was zero and this one was one, right? So the output will become here as one, and here the output will be zero, and here you will have the short circuit. But why will this short circuit happen? That is my question. Where is the short circuit path? Short circuit means that VDD and ground get connected through a low resistance path. Where is that low resistance path?
Sir, here in this inverter, like what you have shown on the screen now, it is like one means we can consider like on that net 5 volts, let us say 5 volts electrical signal is coming, and here 0 means let us say it is some 2 volts signal. 5 volts and 2 volts, these two signals are coming, and these two signals may add up or may subtract, like that may happen.
There will be no addition and subtraction. That is what I want to say. There will be simply a short circuit. And why there will be short circuit? You have to look into the structure of the PMOS, right? So you have to see the structure of CMOS inverter, right? So in a CMOS inverter, you have one something like this, like you have PMOS, you have NMOS, and something like this, right? This is connected to VDD, and this one is connected to ground, right? Similarly, you will have, so this will be the first inverter, and you will have some second inverter, similarly like this, right? Now this is VDD, and this one is ground. Now suppose this one was one, right? So you will have this output node connected through this path, right? The low resistance path, because this is one, this NMOS will be turned on and this output node will be connected to the ground through the low resistance path through the NMOS, right? And for the upper inverter, what will happen, right? In the upper inverter, you will have 0 and the 0 is there. So this PMOS will be connected to VDD and you will have a low resistance path through this. Now, if I connect this to this, right, you have got a low resistance path from VDD to the ground, right? And that's why this is you will have a short circuit, right? So if you connect the output of two CMOS gate, then you can have a short circuit if the inputs are conflicting, or and if you want to connect in this kind of situation, you should have not an inverter but a tri-state. You should have an enable, right? You should have an enable, and when this only one of these enable should be on, and then you will not have a short circuit. That's why the tri-state behavior is important. Okay, any other question?
Sir, if we don't put the tri-state, then output will become 0 now, sir, in this case.
In this case, the output will be undefined because there is a short circuit.
Short, no, sir. In the right side, what you have shown, like in the right side, upper one inverter, bottom one inverter you have kept, and upper one is connecting to the VDD, and bottom one is connected to the ground. And from VDD to there is a path existing to the ground. It means such a output in real time scenario. Is it not 0, sir?
No, it is not 0. Why? Because this node, you cannot consider it to be a 0. Why you will consider 0? If this is a resistance is low, suppose it was say 100 ohms, right? And this one was also 100 ohms, because both are on, right? So this NMOS will also have low resistance. This one will also have low resistance. Very high current will flow through it, and the circuit will get damaged. And the voltage of this will be something between VDD and ground. Why? Because it is a voltage divider. If this you have 100 ohm here, you have 100 ohm here. So this point will be VDD by 2.
Okay.
Right. Now VDD by 2 is an undefined thing.
Yes, sir.
Right. So it is neither 0 nor 1. Yes, or rather than thinking of it, what value it will get, you should protect your circuit, because it will be damaged. Your circuit, because of high current, your circuit will fail, meaning that it will heat up, it will burn, it will just go out of working.
Yes, sir. Thank you, sir.
Okay. Any other question?
Sir, where we have used tri-state in this case?
In this case, we have not used, right? Then you will have a problem. That is what I'm saying. If you have a tri-state gate, then you will not have problem. If you keep this enable as one enable as 0 and another enable as 1, right? Hope I answered your question.
Yes, I got it.
Okay, so let's move now to quickly. I'll go into the Verilog, okay, and describe some basic syntax and semantics of it, and then we'll go into that simulation and other aspects, right? So in Verilog, the modules are the basic building block of a Verilog design. Modules are instantiated inside another module to create a design hierarchy. So as we saw in the yesterday's class, we can create instances inside the module, and module starts with the keyword module and ends with end module, right? So suppose you wanted to create this design hierarchy, right? So you have this module top, right? And inside this, you have instances of mid and bottom 2, right? Mid and bottom 2. And again, inside mid, you have bottom 1. So you have mid and you have the instance bottom 1 here, right? And then you will have this bottom 1 and bottom 2 defined. So this is how you create a design hierarchy. Now, in a module, you will have ports, right? So we saw what are ports in yesterday's class, right? Now, in a module, you can define these ports, the input ports and the output ports. And also in Verilog, you can have in-out ports. And you can also have if you have buses, for example, data bus, address bus, and so on, which is consisting of group of signals, then you can define a range, like a left range and right range, and so on, right? For example, you have in this example I'm showing you, you have a module top, you have input ports defined here, then input port here, and then here you have a bus 320. So this data is basically of 4 bits. So you have data 0, data 1, 2, and 3, right? So and 3. So that's why you have 4 bits here, right? So similarly for counter out, right? So module port names can also be specified here, and direction can also be specified in the module here also, right? Rather than describing separately. Now, ports in a module can be connected in the instantiation in two ways, right? So yesterday also we saw the instantiation, how it is created, right? But Verilog provides that you can make the instantiation by order or by name, meaning that if you don't put the pin name directly, then it will pick by the order. For example, if you are creating an instance of this module mid here in the top module, and you just write C, P in, and P out. So implicitly, C is connected to clock, P in is connected to D in, and P out is connected to D out. This is by order, right? And the other way could be that I say that dot clock, this is the name of the port in the module that is connected to C. So here you are making explicitly connection. And so Verilog provides both of them, but it is always better to make connection by name because it is always easy to debug, right? Later on, because if you add one more port, then you have to put somewhere here, and then it messes up all the instantiations, right? So better to always use a by name rather than order. And then you in Verilog you have a group of statements which are executed, and those you can put inside begin and end, right? So this is known as block. So inside this begin and end, whatever you will be writing, that will be executed sequentially. Okay, those are executed sequentially. These are procedural statements. And this block you can also give a name, right? So now the data types, there are 2 types of data in Verilog. One is the net and the other is register. Now what is the difference between net and register? Can anyone tell me?
Sir, registers data types, there we want them to retain their previous value. Means they must have some memory sort of thing. Even
Okay.
if the input is not applied, that particular output value should be stored for a longer time. And nets, their output should be constantly derived.
Okay.
Output should change.
So now you are correct. But one question is that does register means that you will have memory element in your design? If I declare a register reg
nets
in
is actually for
Verilog,
connection. Register for storing the value, sir.
sorry, can you repeat your answer?
Sir, actually, I'm telling nets are used for connection, and register is nets is used for connection, and register
Okay.
is used for storing the data.
So that is my question. That is I understood, and the other student also said the same thing. My only question is that if you are saying reg is used to store data, then does it mean that your design will always have a memory element whenever you use a reg in your design?
No, sir, it is not that meaning.
Okay, so what does it mean?
It is only for the the behavior, like suppose if we want to have test bench, in test bench we have to give some inputs, so inputs should be held over a period of simulation time. So for that a data type is required which can hold the value over that period of time. So in
Now
such
suppose you are not writing a test bench. So suppose you are modeling a design.
modeling
Yeah.
in that case also, like for example, if you are modeling half adder, in half adder, if you want to model using procedural level, that behavioral level, In that case, this data type is required, because in data type, in behavioral level modeling, this register only can be used.
See, in behavioral model, we also use nets, right? It is not that we have to always use, what I think what you want to say is the procedural block, right?
Yes, yes.
In procedural block, you will always have to need to write to a register, right?
Yes, sir.
So, see, you are somewhat correct, but the main thing is that these registers holding value is for the simulators and to specify a kind of behavior, right? It is not that a register will lead to a memory element, okay?
Yes, sir.
Because this is the most this is one of the easiest mistake that early or beginners of Verilog make, right? They think that whenever someone is writing reg, and reg is a register and register is nothing but a flip-flop, then it should mean that if I write a reg, there should be a flip-flop. That is not correct, right? So nets are basically used for making connections, right? It represents a structural connection. It is a kind of wire. Wherever you write a wire in your design, in your model, then it means you are making a net. It cannot store any value, right? It cannot store any value, meaning that see that where do these values need to be stored? These value needs to be stored by the simulators, right? When you do the simulation, for the declaration of a net or wire, it will not allocate a memory location while doing simulation. Okay, this storing value is referring to that situation, that whether the simulator will store value or not. Okay, so in net, for the nets, the simulator will not store any value. Okay, this is a simple connection between an input to the output, and from one point to another point. Okay, and these nets can be of type wire, supply 0, supply 1, wire and, or wire or. Now, signals that are not declared but are used in connections, they are also of type wire. Okay, for example, if you write a module or instantiation, and here you wrote w1, right? And you didn't declare the w1, so w1 is declared here, but here w2 is not declared anywhere, right? So if you don't declare a connection in, or the name of the connection, then implicitly the tool will assume it to be of type wire, that is 1-bit net. 1-bit net it will assume, right? So, but it is always better to declare wires rather than allow the tool to implicitly infer those things. Okay. Now, what about the registers? Registers represent variables that store value. Now, where do these values need to be stored? While doing simulation. Okay, when you are doing, while the tool is doing simulation, then for a reg declaration, suppose you write reg M1. Then for this M1 reg, the simulator will internally allocate a memory location M1 where its value will be written and from where it can be read, right? So this is why what is meant by storing the value. It is not that your design will have a memory, this is your design which you are modeling. It is not that your design will have a memory location as M1. That is not correct way to think. The correct way to think is that there is a simulator. The simulator has got a various memory locations, and whenever you declare reg M1, then this simulator stores or allocates a memory location named M1 while doing the simulation. Okay. So registers store last value assigned to it until it is changed by another statement. So one statement assigned, then it is holding the value in the simulator unless and until some other statement comes and then assigns itself. If a signal is assigned within a procedural block, meaning that if you have a begin block, end block, or if you have an always block or initial block, then here you have to declare whatever the signals are written here. Those written the value at the output, those should be of type register. Okay, and you can have array of registers can be created by for example, I can create 0 to 3 like this, right? I can give the vectors and so on, right? So for example, in this example, for example here So here we are basically see that we have declared a register reg p out, and inside this procedure statement we are writing p out. If suppose I would declared here wire p underscore out, then this code will not work as per the semantics of Verilog, because anything written inside a procedural statement must be of type reg or integer. Now there are two types of block. One is the initial block and the other is an always block. These are used in modeling design in Verilog. So blocks starting with initial block is executed once at the beginning of the simulation. If there are multiple initial blocks, all of them are executed at the beginning of the simulation time. Okay. Now which one will execute first? If you have say 10 initial blocks, right? So which of these initial block will be executed first? Any answer? Suppose I have a module. Inside this I write this is how we write initial block. You have initial block like this. It will be executed once, right? All of these block. Now if you have say 10 initial blocks inside module, which of them will be executed first?
Sir, it is not known to a designer.
Yes,
because
you are correct.
sometimes
So,
it may first statement, sometimes the last statement.
yes. So we said that HDLs are used for modeling hardwares, right? And hardware runs in parallel. Now if you have a hardware, you have an input here and you have multiple blocks. Now if I ask you the question that if I apply an input, which of them will start processing first? What will be your answer? What will be the answer? If you have an hardware, right?
Yes, sir. So
What
no
will
one
be the
knows, sir, which one is first.
Yeah. So see, in real circuit,
So design not which one is
yeah.
first.
So in real circuit, what will happen is that the one which has got the least delay, that will start processing first, right? The one which has got the least delay at here in actual circuit. But that behavior you cannot ensure. Why? Because of many reasons, and one of the foremost reason is the process induced variation. Process induced variation, because once you fabricate it, the behavior of this wire is not totally under your control, right? And therefore you cannot ensure that if you have made a wire interconnect or metal wire in your layout, where the signal will reach first, if all of them are of same length. Depending on the process induced variation, some block will be executing first and then the second one, and so on, right? And the same behavior is basically modeled by this hardware description language. If you have multiple initial block, you don't know which one will be actually executed first. So, and that's why the simulator has the freedom to choose any of the initial block. If you have 10 initial block, any of them will be executed first. Okay. And these initial blocks are very much useful in the test benches. You initialize your design to certain state or initialize your signals to certain state. So for those purposes, these initial blocks are used. Okay, but these initial blocks are not that much not synthesized. Okay, those are not synthesized. We'll look into that later. And another type of block is an always block. You have an always block. So in a block starting with always is an always block, and always block executes throughout the simulation. Initial block executed only once. Once it executed, finished. It will not be seen again in the simulation. That's it. For the initial block. But for the always block, what happens that the simulation is done or it is executed throughout the simulation. Oswell block has a sensitivity list that specifies when to execute that block. Okay, so you have a sensitivity list. So this is your always block. This is your always block, and you have got the sensitivity list. And this sensitivity list says that when should this block start? When should this block execution start? Right. So when we write always at A or B or C, it means that whenever there is a change in the value of A, this block will be executed, or there is a change in the value of B, or a change in the value of cell, any signal named cell, then this block will be executed. It is similar to modeling a circuit. For example, if you have an AND gate, when will this AND gate produce a new result? Whenever the input will change, right, you will see the change in the output. And so similarly, if you have any change in the input, the output will change, right? So this kind of hardware behavior is modeled through always block. So there are two types of sensitivity lists. One is level sensitive, which is shown here, and there is edge sensitivity, in which you can write pauses or negatives, right? So that is known as edge sensitivity list. So whenever you have edge sensitivity list, then you will have flip-flop inferred for that. And whatever is specified after ampersand, what is denotes the triggering condition for the always block. In an always block, only reg kind of signals or reg or integer data type signals can be assigned. You cannot have a wire here. If you have written somewhere inside this procedural block, then that should be declared as register and not as the wire. Okay. Any questions till now? Okay.
Sir, repeat the always begin, sir. Just sensitivity list.
Sorry, can you repeat what you asked?
Always begin, sir. Model, you can just repeat, sir, this part.
Okay, so there is a kind of statement which is known as always block that is supported in Verilog. And what is the meaning of always block? It contains a code which needs to be executed throughout the simulation. Okay, for example, if you have an AND gate, right? So in an AND gate, the value of the output will be changing whenever the input is changing. So to model this kind of behavior, you have to have something in your hardware model which kind of captures the situation that it will compute always. Whenever the simulation is done, it is computing always, right? So that kind of semantics is or that kind of behavior is modeled using the always statement. Now always block has got the sensitivity list. So there are the sensitivity. So whatever we write after ampersand, this ampersand, that part is known as the sensitivity list, right? Now this sensitivity list can be of two types. One is level sensitive and other is edge sensitive. So in level sensitive sensitivity list, you don't have this pause edge or negate, right? Keyword. So this is a level sensitive and this one is edge sensitive. Now this level sensitive will model a combinational circuit element or a latch, right? We'll see that later on. And edge sensitive list will model a flip-flop. Okay, and whenever we drive write a Verilog code, then whatever is written, that should be declared as reg or integer, and it cannot be of type y. Why? Because while doing simulation, the code, it needs to basically execute this code multiple times, and the simulator needs to hold the previous value, right? And to hold previous value, it must have some memory location. And how does a simulator get a memory location for simulation? Through the keyword reg, right? When you declare a type reg, then only the simulator will have a memory location. Okay. Any more question?
Hello,
So
sir.
two people write.
Sir, is it possible?
Sorry.
Sir, is it possible to exchange information between these always blocks? Like
Yes.
some of first always block is get
Right. So
then how?
it can happen that you write some value to y, and the other always block is sensitive to y, right? So when y gets written, the other block get triggered, right? It can always happen like that. Okay. For example, consider this AND gate. This AND gate will be driving some other AND gate, right? Now, whenever this output changes, the other AND gate should also evaluate, right? And its output should change. So you will have a situation in which you have always block for the first AND gate and then always block for the second AND gate. This is one way in which it can be. So I'm just giving you a description. It is not that this is directly used in modeling Verilog, but I just gave you an example where the information or the written value of one always block can be reused, or rather it can, the change in the value of always of a signal in an always block will trigger another always block. Okay, and then another always block can again trigger another always block, and this is how the simulation will progress, right? And this will go on until the end of the simulation time that you have specified. Okay, any other question?
Yes, sir. Yes, sir.
Okay, so now this the edge sensitive keyword is pause edge. Similarly, you can have neg edge. Okay, now pause edge is used to model this kind of situation, right? Whenever your signal rises from 0 to 1, for example, a clock edge which is rising from 0 to 1, then it is known as pause edge. But understand that Verilog is not a Verilog supports four kind of logic values. It supports 0, 1, X, and Z. Okay, X and Z. These are four different values which are supported by Verilog. So when the signal is either X or Z, that is also taken as X or Z. That is treated as a pause edge, right? And if a transitions from 0 to X or Z, that is also taken as 0 to X or Z, that is also taken as a pause edge, right, in a four valued logic. Similarly, the analogously you define for the neg edge. Okay, and then multiple, you can in a code you can have multiple always an initial block, right? So you have initial block, you have always block, and another always block. Now which of these block will be triggered first? Suppose you have a module in which you have one initial block and two always block like this. Which of them will be triggered first?
So they will execute concurrently.
Right. So yeah, any of them can be executed first, right? This is how the parallelism in hardware is captured in the language. If there are multiple always an initial block in the same module, then all these modules start executing at the start of the simulation, and all these blocks execute concurrently. All three blocks execute concurrently in the example shown. And you as a designer, you don't have a control which one will be executed first. The simulator will decide on its own in an arbitrary way, and your circuit should work in that manner, or should produce a correct result irrespective of what the order is chosen by the simulator to simulate it, right? So this is what it basically ensures is that if you actually make that hardware, your hardware is designed properly, and it is not dependent on the order of execution. It is independent of order of execution, right? And that should be how the hardware be designed, because if you have multiple blocks of hardware in running in parallel, you cannot control which one will be executed first, right? If you want to actually control it, then you should say that, okay, this is my block which will be executed first, then the output of this goes into the next one, and so on. And if there is an order there, and then you have to say that in a particular way that this is that the sequential block of code will be executed in that particular manner, right? So there is a way in which a sequential operation can be specified in hardware description language. Anything that you specified within begin and end, those are executed one by one, okay, as in a general programming language. So you can use this feature to order the sequential circuit, right? You can order a sequential circuit by putting them in the begin end block and ensuring that your circuit behaves correctly in that. Okay, now there is a statement in Verilog which is known as assign statement, right? So this assign statement is used to continuously drive a net. Y is a net, right? It is not declared as wire, but for an port it will be implicitly declared as wire. and there is no sensitivity list, and it models a combinational circuit. Now there is another kind of state of assignment which can be used inside your procedure block. Procedure block meaning inside initial block, inside always block, and and there are two symbols. One is equal to, and the other one is less than equal to. Okay, so this one is known as blocking assignment, and this one is known as non-blocking assignment. Easy way to remember that which one is blocking assignment is that the word blocking is small and the symbol is also small, and word non-blocking is a bigger word and you have a symbol also as bigger word, right? So this is a way to remember that which one is blocking and which one is non-blocking. Now these two kind of statements are, or these two kinds of state assignments are executed in different manner. Okay, and these are more this feature in Verilog is provided to distinguish between a procedural statement and a sequential statement. Sorry, a sequential statement and a concurrent state. Okay, now how is the blocking assignment executed? A blocking assignment is execution is in blocking assignment, the execution of the next statement is blocked until the current statement is executed. Okay, this is how the blocking assignment means. So you have one statement, you have another statement, third statement, fourth statement, right? So if all are this blocking statement, meaning that they are the LHS and RHS between them, you have this symbol equal to, then this is a blocking statement. It means that once this statement is executed, it gets completed, then only it goes to the next statement. Once this one is executed, then it goes to the next statement, and whenever this executed, then the third one, right? So execution of next statement is blocked until the current statement is executed. This is how the blocking assignment work. It is similar to the traditional programming language like C or C++, Python, or whatever you might have studied. Okay, now in non-blocking assignment, what happens is that the execution of the next statement is not blocked. Is that not blocked until the current statement. So suppose you have an LHS and you have less than or equal to RHS, right? So you have this kind of statement. Then you have another kind of statement, LHS, and you have another RHS, or rather say this is LHS1, this is LHS2, this is RHS2, and this is RHS1, and this is RHS2. There are two statements which are non-blocking. So what it means is that when this statement is executed, the first statement is executed, only the right part, only the right hand of this assignment, the non-blocking assignment is executed. Not the LHS is not yet updated. It is not updated, and it goes to the next statement. And in the next statement, only the RHS will be evaluated. Okay. Remember that this RHS can be an expression, for example, A and B and C, right? So whatever the current value of RHS will be there, it will be evaluated, irrespective of whatever. So whatever the current value of A, B, C is there, RHS is evaluated and its value is kept. Okay. And once these two statements are, the RHS are evaluated, then it goes and updates this LHS1 and LHS2 with whatever was already evaluated. So RHS1, whatever was evaluated, it will simply get updated to LHS1. And similarly, what was the RHS2 was evaluated, it will be simply updated to LHS2. Okay, so this is how the non-blocking assignment is executed in simulation. It is executed in two parts. One part is that the RHS is evaluated, its value is computed, its value is stored, 0 or 1, whatever the value is, that value is computed, and for all the non-blocking assignment, all the RHS will be executed first, and when the simulation time is about to end, then all these value which was computed of RHS, it will be simply put to the LHS. Now, when I mean to say, when I say that the whatever the RHS was evaluated, it will simply be it will be put to the LHS. What it means is that if the value of a signal changes in LHS, the RHS which were evaluated and kept earlier, that is not going to update. For example, suppose here your signal was A and B and C, right? And here the value was say Y and X. Now, suppose your LHS was Y and this one was Z, right? Then you, whenever RHS changed, sorry, RHS value was there, RHS was evaluated, that is A and B and C, right? That will be evaluated and that current value, that value will be stored, and Y is not yet updated. And whatever the Y was for current value, that will be assigned to the RHS2 and kept. After the updation phase, this Y will be changed, but this RHS2 will not be changed, right? Even though it depends on Y, right? And that is why the non-blocking assignment is distinct or different from the blocking assignment. Okay, so let me give you an example, then it will become clear. Okay, now this is suppose you have an initial block, two initial blocks. In this, the first initial block, you have a blocking assignment. You have blocking assignment, right? And in the second block, you have non-blocking assignment, right? Now, if this is a situation, right? Now, tell me which when will A, B, C be evaluated or will be changed, and when D, E, F will be changed. Look at this code, take some time, and then tell me the answer, that when will A, B, and C will be updated to their respective RHS, right? And when will be these A, D, E, F will be evaluated, will be updated. If you have the answer, just raise your hand. I will ask you. Okay, Devi Chadda, please answer.
Okay. Sir, the first initial block that has blocking assignment statements, A will update in 10 seconds, B will be, depending upon the time scale, B will update in 20 and C will update in 30, whereas D, E, F will update in 50 nanoseconds or seconds, depending upon it.
No, I don't think that is correct. Okay. So any other participant? Raju.
Yes.
Yeah,
Yes,
Raju.
sir.
Yes.
Sir, actually non-blocking assignment. It will A will happen after 10 seconds and B will after 20 nanoseconds. 20 seconds.
Okay, just hold on. A, B, C is blocking. It is not non-blocking.
Sorry. Blocking assignment. Yes, sir.
Yes. Go on.
A will after 10 second, 10 second. B after 20 nanosecond and C will be after 30 nanosecond.
Tell me the exact time when B will be updated and C will be updated.
After 30.
B will be updated after 30, right?
B will be after 20. C will be after 30, sir.
No, that is not correct. Any other one? Any other student want to answer?
Sir, A at 10 nanoseconds, B at 30 nanoseconds, C at 60 nanoseconds.
Okay. And what about D, E, F?
Yes, sir. Yes, sir.
Sorry, what about
Sir,
D,
D at 10 nanoseconds.
Yes. E?
Sir, D at 10 nanoseconds and E at 20 nanoseconds. E.
Okay. And F?
Because it gets only 10 second delay, and okay. F will 30 nanoseconds.
Yes, you are correct.
It means
you are correct.
Yes,
okay.
Yes.
So let me now explain why it will happen like this. Okay. So see, blocking assignment is similar to your general programming language like C, C++, whichever programming language you are exposed to. So one statement will be executed, then the next, and then the next, right? So the A will be executed after 10, right? Now B will be executed. The delay is 20, meaning that 10 plus 20, that is after 30 time units, B will be updated. Now, once B is done, then the C will start executing, and there you have a delay of 30, right? So 30 plus 30, 60. So C will be updated after 60 at 60 time units, right? Now, what about non-blocking? In non-blocking, this one, the RHS of this is evaluated and at 10, and then and it is kept. It is kept whatever, and so whenever here you have all these as non-blocking, right? So when it goes to the first statement, the D assigned to one tick B1, right? It is in non-blocking, it is not waiting for this execution to complete. Okay, it is not waiting for this execution to be complete, and it moves to the next statement, E. And again, when even if E is not yet completely, or this statement is not completely executed, it moves to F, right? And when E is computed, what is done? What is done actually? So when okay, so when when E is evaluated, sorry, when D is evaluated, then only the RHS part is evaluated. That at 10 time units, the value of D will be value of one tick B1, right? That is 1. And then in the second statement, what it will be in the when RHS is evaluated, what will happen? It will say that after 20 time units, I have to assign it to the value one tick B0. And F, for when we execute this, or the simulator executes this statement, then the simulator will say that in the RHS means that after 30 picosecond or 30 time units, one tick B1 needs to be assigned to F, right? And whenever these time units, the time reaches in the simulation, this D, E, and F will be updated. So in this case, it will be it looks like a kind of parallel operation. Like this is a kind of parallelly, all these statements are being executed parallelly. So this is how the non-blocking assignment will be executed in simulation, right? The RHS will be evaluated and kept. And similarly for RHS will be evaluated and kept, RHS will be evaluated and kept. And it will not wait for the execution to complete before moving to the next stage, right? That is what non-blocking means. Okay. So any questions? This is one of the most important concepts for Verilog, that how the blocking assignment and non-blocking assignments are executed. And many a times you will in interview you'll face questions related to this. Okay, so if you have any doubts, please ask. Okay, so let me move further. Now Verilog supports functions and tasks. Okay, so if you have a group of code that is doing something, you can put it inside the function. The difference between function and task is that in function you can have only one output. Okay, and it can have one or more inputs, right? But it should have only one output. In task you can have 0 or multiple inputs, outputs, and in-outs. Now you cannot have delays and pauses, negate inside functions, but you can have those in tasks. In functions you can have it is used to model combinational circuit, and tasks can be used to model both combinational and sequential circuit. And a function can call another function but cannot call other tasks, and task can call other tasks as well as function. Okay. And there are some system define or some functions which are already available for us to use, and these are very much useful in simulation. For example, you use the function display, probe, monitor, stop, finish, reset, random, time, and there are many more. You can look into the map. Okay, so any questions till now what we have discussed? So let's take a break of 5 minutes, and let us meet at say 10:50. Okay. Okay, so let's restart. So any questions from what we have discussed so far?
Yes, there is a small question.
Yes.
Sir, you said if we keep blocks, like always blocks in a begin and block, so they will be executed sequentially. So means, is it going to happen like they will be executed sequentially?
Yes.
Okay, sir. And the next question is, sir, I have seen at many spots in the sensitivity list, they write always at the rate star. So
Right.
what does that star indicate significance?
Okay. So always at star means that whatever is on the RHS of the statements, right? So if you write always at the rate star, right? So we will discuss this. Okay, so let us take it in subsequent discussion. Okay. Any other question? So I will discuss this in the next set of slides. Always star. Okay. So any other question? Okay, so let's move forward. So let's look into the RTL simulation. So RTL simulation is performed to verify that the output generated by a design is in agreement with the desired functionality. So this is basically the most important technique to do the functional verification for your circuit or your design, right? So what is the how do we do this simulation? So you need to provide some test vectors as an input to your design. Okay, so you provide test vectors to the design and run the Verilog simulator, and the simulator will give you an output response. And then you compare the output response to the expected response and see whether it is matching or not matching. And depending on that, you decide whether your design is correct or wrong, right? So this is what the purpose of simulation is, right? So input stimulus is applied to the design, response of the design is computed, and the computed response is compared with the expected response. If the computed response of the design and the expected response match, then the verification of design is set to pass, else it is considered to fail. And now to give this stimulus and other things, what we do is that we create a test bench. We create a test bench to do the simulation and do functional verification of our design. So there can be many different ways in which we can implement a test bench. One of them is like this: you have a bigger module, okay, or bigger module or entity. Inside this, you have some mechanism to generate stimulus. Okay, so this is the generating the stimulus, and you instantiate the design. Whatever you have designed, whatever your design is, you instantiate inside your test bench, and you apply the stimulus to your design. So which you are basically testing, and then you observe the signal that is coming out of this test bench. Okay, so either this signal can be written to a file, or you observe the waveform and other things, and this you get the test result. And this test result is compared to the expected behavior, and based on that we say that our model or design under test is passing or failing or so on. Okay, so this is how the simulation is done. So now I'm showing you how to write a test bench. Okay, so suppose we have made a design of a counter. Okay, so this is a counter in which you have clock signal, that is the input signal, and then you have a reset signal, and you have enable signal, and this is the output of the counter. So it is 4-bit output, so it is counting from 000 to 1111, right? That is how it will do. Now suppose you start with when you reset, give a reset signal of 1, then whenever reset is made 1, then what happens is that this output of the counter goes to 0. It goes to a 0 of a delay of 1 time unit. And then when this reset is equal to 0, meaning that it is deasserted, then whenever and if enable is made 1, then your whatever the count was, it will increment to 0 0 from 000 If it was, then it will become 0001. And then in the whenever next clock, so everything is put inside the always block, and which is triggered by a clock. So this block will be executed only when clock signal is coming, right? So whenever the clock signal will come, this block will get executed. So whenever next clock will come, then it will go to 0. If the enable is high and reset is high, both are high, meaning the reset is reset is low and enable is high, then the counter will actually increment to 0 from 001 0001 to 0010, and then to 0011, and so on. So this is how the simulation will progress. Sorry, the design will keep on counting. Now, how to write a test bench for it? So there can be many ways to write a test bench. A systematic way to write is that we do 5 things in a test bench. First, we initialize the design. We keep the signals to the initial conditions, and then the second thing is that we generate the signal, generate the test signal. We generate the test signal that we want to test our design with, and then we instantiate the design. And then when we instantiate the design and we generate and apply this test signal to this DUT, then DUT will produce some output, and we monitor that output and save it in a file or see the waveform, and then finally we end the simulation. So these are 5 steps that needs to be done in a test bench. Now for our counter, now let's see how we can accomplish all these 5 tasks. So first we initialize our design. We say that my clock is 0, my reset is 1. I'm asserting that or reset is becoming active, and therefore counter output will be 0000, right? And we enable make it enable 1 throughout the simulation, and then after 20 time units we say that now reset is deasserted. Now the enable is active and reset is inactive, right? So this is how we initialize our design, and then we generate the test signal. Now for a counter, the test signal is only the clock, right? So we write that clock is changing to not clock after the delay of 10. So you will have 0, then after 10 time units it will become 1, then after 10 new time units it will become again 0, and so on. So you will have a kind of clock signal like this, right? And then after this you instantiate the design. So you instantiate the counter, right? We saw a counter in the next. So you put the name of the module, instance name, and you connect these signals that you have created in your test bench to the ports of the design, right? You are making connections here. Okay, and then you store the output in the file counter.bcd, from which you can see the waveform and other things, do the post processing, and also you monitor the signals. These are which signal you want to see: clock, reset, enable, and CC is basically the output, right? The output of the counter. We are seeing the value, and finally you end the simulation. So I will suggest that if you have not run this test bench by now, please run it and see for yourself that how it is working. Okay. So okay. So any questions that you have regarding test bench and simulation? Okay, there are no questions. Let's move to the RTL synthesis. Now let's understand that if we write an RTL model, how it will get synthesized. Okay, how it will get synthesized, what instances will be there, right? So first of all, you should understand that some constructs in Verilog are not synthesized. As we started the discussion, we said that Verilog was designed for simulation. It was not designed for synthesis. Okay, so the constructs in Verilog there are many constructs in Verilog which are there existing for supporting the simulation. Okay, but synthesis was developed later on. Say Verilog was invented for simulation in early 1980s. Okay, and synthesis was developed in late 1980s and early 1990s, right? So the synthesis was developed much later than simulation, and therefore many of the constructs which are there existing in the language, which are more for the purpose of simulation rather than synthesis. So several constructs of Verilog are ignored by the synthesis tool. Now, what are these constructs? For example, you have this initial block that will not be synthesized in Verilog. You don't synthesize whatever is written in Verilog. Then there are display, monitor statements, fork, join statement, force release statements. These statements are basically not synthesizable. These are not supported by synthesis tool. They will simply ignore these statements. Then other thing to note is that wherever you write delay statements, so these delay statements are basically for simulation. These are not for synthesis. Why? Because synthesis is producing a circuit for you. It is creating a schematic or the netlist for your circuit. It's creating your design. But in a design, you can never ensure that your delay will be exactly same as what you are specifying. For example, I'm saying that my delay should be 10 time units, right? So from the synthesis perspective, you can never ensure that your circuit will have exactly delay as 10 time units, right? That is very, very difficult to achieve. Why is it difficult to achieve, say, an exact delay in our circuit? Any answer?
Sir, process variation.
Yes, one of the reasons is process induced variation. So even if you design for, say, 10, if because of the process variation, it will become 20 or not 20, maybe 11, maybe 9 or something, right? It will vary statistically around this value. If the average value, you can say that, okay, it will be 10, but it will vary around some value, right? It is from the circuit perspective, you can never ensure that the delay is exactly that, right? So how do we design our circuit? So if we are not able to ensure a delay, the value of our delay in our circuit, then how do we design it? See, this is a very basic problem. If you cannot say that my delay is this much, then how do we design a circuit? Or any digital circuit or any integrated circuit? Any comments? Okay, so see, in all the design process, what we designed is not for a particular value. So when we don't design a circuit to operate at, say, or produce a delay element to have an exact delay of 10. We always design within a range. Okay, we say that the delay of this circuit element should be within, say, 8 nanosecond or time units to 12, right? So we always design within a range with some margin, right? And that is possible, right? And that is what is ensured also by static timing analysis that we'll be looking into in tomorrow's lecture. So we always design a circuit to have a delay within some range, and that is not impossible. That is very much possible, and that is what we do, right? To ensure that our design will say that the average value will be 10, but it will vary between 8 to 12 with this probability and so on, right? And that is what we designed our circuit with, and this is easy to meet. And this is an important concept of this design flow, that we design for a given range with some margin, and that margin should be some reasonable. It shouldn't be very wide or it shouldn't be too narrow, right? And that is an engineering decision that we need to make. Okay, so if you write a statement like out1 assign to A after a delay of 10 time units, then what the simulation will do, for simulation it is just a number, right, in its data structure. So simulation will treat it exactly as a delay of 10, right? So it is for the tool, it is very easy to just say that okay, so whether so to give a delay to a signal by this much amount, by it can do in exactly in the same way, because it is just mimicking the circuit. So simulator will take a delay of 10, but what synthesis will do? Synthesis will simply ignore it. Okay, it will simply ignore this delay of 10 and treat that statement as out1 is assign a value of 8. Okay, so these delays are not supported in synthesis. It is supported in simulation, but ignored in synthesis. Okay, any questions? Okay, so now the how are these continuous assigned statements assigned statement synthesized? It will be synthesized to a combinational circuit. For example, if you write out one, in one, and into, you will have a circuit like this: in one, into. Okay, and this. So in the subsequent slide, what we are discussing synthesis of RTL constructs. So we'll be looking at various RTL constructs. For example, this is an RTL construct and how it will get transformed to the circuit, right? So if you write something like out one is equal to in one and into, then it will get transformed to an AND gate, right? Because you have, because of this operation, right? Now, if we can model this kind of AND gate or so is using an always block also, and in this always block, it should be level sensitive. It should be level sensitive. So we use a level sensitive always block, and that means that we don't use pauses and negate. Then only we'll get a combinational circuit, right? So if you want to model a combinational circuit, we shouldn't use pause edge or neg edge in the always block. It should be level sensitive, and it should you should write to a reg, because inside and always you are allowed to write only to a reg or an integer. So out one is reg, right? And then you use in the sensitivity list, you put all the input signal in one and in or into, and you will say that out one and you assign out one to in one and into. So in this case also you will get a same kind of circuit as for the assigned statement, right? You will have in one here, you will have into here, and you will have out one, right? So this is how your circuit will be synthesized too, right? Any questions on this? So here you can see that even if you have written an always a reg, right, you'll get a combinational circuit rather than a sequential circuit. So reg doesn't mean that you'll have a flip-flop in your design. Any questions? Okay. So using we can use continuous assignment to model multiplexer. So you can write Z is equal to cell, then A, else B. So you will have a multiplexer, meaning that you will have cell here. If cell is equal to 1, then whatever was at B, it will go to the output, right? Z. And if it was 0, then it will go, if cell, then A, right? So when it is 1, then A should pass, right? Not B. And when it is 0, then B will pass. So B will be here. Okay. So this is how it will be synthesized. And you can use either if statement or case statement to model the same thing. For example, you can, if you want to use if statement, then you write if cell, then Z is equal to A, right? If right, and else B, right? Else if else B. So you'll get similar, the same kind of circuit. And using a case statement also, we can get the same behavior, right? So we say that you have always inside, you have the sensitivity list as A, B, or cell. So whenever anything of this changes, then this block will get triggered, this always block will get triggered. And if cell is equal to, depending on the value of cell, if it is 1 tick B 0, meaning it is 0, then you'll get A, right? Okay, otherwise you'll get B, right? So you will get a kind of multiplexer behavior in this case also. Okay. Now, if you want to model a sequential circuit, then you should use pause edge or neg edge. Okay. So for example, if you want to model a flip-flop, then you should write pause edge clock, then Q is assigned to a value of D, right? So you will have, in this case, you will get a flip-flop, you have a clock signal, right? You have clock here, and on the D pin, you will have D, and here you will have Q, right? Or Q. So this is how it will be synthesized to. Now, if you want to have a asynchronous reset, meaning that you have also a reset signal here, and whenever reset is equal to low or and it is S sensitive, then you put negate reset there, right? So if you put negate reset here, negate reset, then it will create you an asynchronous signal, meaning that either pauses clock occurs or negate negate reset occurs, this block will execute it. So whenever negate reset is there, there is a higher whenever there is a negate reset, then the Q gets the value of 0 and the output is reset. Otherwise, Q will get the value of D. So the reset is getting a higher preference in this case, depending on the reset value. If it is 0, so it is negate reset, right? And then you are basically whether the value of reset is 0 or 1, you are assigning its value, the output of assigning Q to 0 or the value D, right? So this is a kind of asynchronous reset flip-flop. Now, what is a synchronous reset flip-flop? Okay, so flip-flops with synchronous reset can be modeled by not mentioning reset in the sensitivity list. So synchronous reset are used to. So what is difference between synchronous reset flip-flop and asynchronous reset flip-flop? Can anyone tell?
Sir, on the perspective of the Verilog code or
Any,
functionality?
no, any in just functionality. Not from Verilog perspective, just tell me the difference between a synchronous reset flip-flop and asynchronous reset flip-flop.
Okay, sir, asynchronous reset occurs even if reset is triggered. The reset signal changes even if there is a positive or negative edge of clock is not there, even if it's not there. But synchronous will only happen if there is clock triggering.
Right. So in synchronous reset, what happens is that the output changes or it is reset to 0 only when clock triggering happens, right? So the change in is, you can assume something like this, right? So if you have a clock, right, and you have an AND gate at the input, right? So if you have a reset here asserted, either it is positive reset or negative reset depending on the functionality, then this D will change and the output Q will always be synchronized with respect to this clock, meaning that the output will change only when the clock edge occurs, right? It will always change at this edge. It will not change at any other time. So the output will always be changing at the clock edge in a synchronous reset flip-flop, right? And in asynchronous reset, the output can change anywhere. Whenever the reset signal is asserted, suppose it is asserted this point, the output will change to 0, right? That is what asynchronous reset is, right? So if we want to model a synchronous reset flip-flop, then then we need to put the reset inside the always block of which is triggered by clock, right? So here earlier we had or neg edge reset, right? So we are not writing that. We are not writing the neg edge reset here, and this reset is happening only when the clock edge is occurring, and that's why it is a synchronous reset. Okay. Now, how are latches modeled? Okay, so now let me ask a very simple question. Many students get confused in this. So what is the difference between a latch and a flip-flop? Who will want to? Yes.
Latch is yes, level triggers. Flip flop is edge triggers.
Right. So this is correct answer, but many a time students make mistake just in this simple question. So suppose you have a flip-flop. So the output will change only when the clock edge occurs, right? In a flip-flop. And if you have a latch, then output can this D, if output can change whenever enable is equal to 1, right? Or so if you have Q and if you have the enable signal like this, enable signal is like this, then in this time whenever enable is 1, if the D is changing, your output will change within this time. This is the behavior of a latch. Okay, this is a variable of a latch. For a flip-flop, even in this time duration, if the D is changing, your output will not change, because output changes only when the clock edge occurs, right? So this is the basic difference between a flip-flop and a latch. Now, the signals in the sensitivity list should only be level sensitive for a latch. If you want to model a latch, the signal should be level sensitive. It cannot be edge sensitive, because if we write pause edge or neg edge, it will become a flip-flop. Okay, there should be a conditional write on the output register. This is the important thing, that the for a latch, it should have a memory, right? So if in the latch, if enable is equal to 0, right, in that case, in this region, when enable is 0, the old value of D will be retained, right? It is a kind of a memory element. Enable is, so whenever enable is equal to 0, whatever the Q was there, it will be retained, right? And even if D is changing within this time, within this time frame, right? So let me draw a better figure. Suppose your enable signal is like this in a latch, right? So even within this time, see, if D changes, nothing will change at the output. So latch is a kind of memory element, and therefore there should be a conditional write on the output register, meaning that the condition should be that in this region writing will happen at the signal, and in this region the writing will not happen. So there should be some condition under which it should be written, and some condition under which it should hold the previous value, right? So this is how we model a latch, right? So in the latch, you have enable signal or D, right? So it is not only dependent on enable, it is all this always block should also be triggered by D. Again, this is a mistake many new beginners of Verilog make, right? So in the always block, you should have not only the enable, but you should also have a D in the sensitivity list. Why should you have D here? Any answers?
Sir, what is D, sir?
D is the data. If you have a latch, you have three inputs, right? One is enable, one is D, and other is Q, right? So these are three inputs. Now this D, I want to model this kind of behavior of a latch, right? So this model is basically trying to capture a latch or model a latch. Now what I'm saying is that if you want to model a latch, then we'd have to write an always block, and in this always block, I should have enable signal and also D signal. Why should we have D signal? Remember that in flip-flop we didn't have D here, right? We had only pause as clock. That was sufficient. But why do we want to have D here in the sensitivity list in the always block for a latch? Any answers? So we want this D because whenever enable is 1, suppose enable is 1, then whatever the change happens to D, that must be captured at the Q, right? So suppose you have an enable signal like this. This is your enable signal, right? So when I say enable at always at enable, then whenever the enable changes, right, this block will be triggered. So whenever it becomes from say 0 to 1 or 1 to 0, this block will get triggered, right? Now we want that whenever enable is equal to 1, Q should be the output so the input D should become to Q, right? Now suppose in this the D was like this. the signal was like this. Now we want that the Q should be that whenever the enable is 1, the value of D should be captured, right? So we want that, suppose Q was initially 0, right? So whenever this enable became 1, the D will become here. D became here. D became D. Sorry, Q became D. Q became so Q became so whenever enable was 1, whenever enable became 1, whatever was at D, Q will get that value, right? So it was 1, so it will go reach 1, and then whenever D became 0, it should be captured at the output, right? So this transition should also be captured. Now, if we don't put here D in the sensitivity list, this transition will not be captured at the Q, right? And that's why we need to have D also in the sensitivity list when we model a latch. Okay. So when we write a model a latch, we should have enable signal as well as D signal. And there is a conditional, right? If enable, then Q gets a value of D, and meaning that if enable is 0, then nothing will happen. Nothing will happen, meaning that the Q will retain its old value, right? And so whenever enable is 0 in this region, whatever the value of Q was there, it will retain the value, right? And that's why there is a latching action. Latching or retention of state will be happening in this flip-flop, right? So that so for modeling a latch, we should have a conditional, right? And under some condition, there shouldn't be a right, and that condition is enable is equal to 0. In that case, Q will not be written anything. It means that it is holding the previous state. Okay. Now, what happens many a times that many a times it happens that we are accidentally model a latch rather than a combinational circuit. Many a times we want to model a combinational circuit, but accidentally we model a latch, right? So suppose we write this code, right? We write this code. We wanted basically to model A and B, right? We write an A and B. And so we write this code A or B or right. And we say that if right begin out is equal to A and B. And now what will happen? What will it synthesize to? Any answer? Now, what will be the synthesis of this Verilog code? So in this case, you can see that if right is equal to 1, then something is written to out, right? And if right is equal to 0, then the old value of out is retained, right? The old value of right is retained, right? And therefore, this is a kind of a latching action. But it may happen that we miss the else condition, and that's why this code is being so this will be inferred as a latch, right? So if we don't write in the else condition, if we write the code as it is, then it will be synthesized to a latch in which you have enable here, right? And here you will have right. Whenever right is equal to 1, then you are getting a value of A and B. So you will have the value as Q, right? And this Q will be going to output, right? So this is the Q pin of the latch, and this is the output. So whenever right is equal to 1, then A and B will be produced at the output. And whenever right is equal to 0, what will happen? It will retain its old state, right? And that's why we need to have a latch here. If you cannot have a combinational circuit, it will retain the old state. And to retain a state, we should either have a latch or a flip-flop. And since this is a level triggered, it should have a latch. Okay. For the conditional branch where So for the conditional branch where the output signal is not assigned a value, it implies that the output signal retains old value and a latch is input. Okay. So suppose we wanted to model a combinational circuit and wrote a case statement like this. And we got and it will be this one will be inferred as inferred as a latch. Why? Because there is the for the case to tick B11, we have not given anything, we have not written anything, right? So if that is the case, then this will be a latch will be inferred. Now, if we actually want a case statement to model a combinational circuit rather than a latch or flip-flop, then what we should do, we should add a default statement. Okay, so how to ensure that no latch is inferred for the case statement that is intended to model combinational logic? We should use a default statement. So here we should say default, and in that case what the value is. Then all cases will be covered. In all cases out will be written, and therefore the no memory action is required. Okay. Another thing you should note is that many a times we have to write big sensitivity list. We have to write all the signal name which are on the on which the output or the output variable depends. So in this case there are 3 inputs, so we write A or B or C. So it may happen sometimes that we miss some signal, right? If the list is long, suppose your always block is big and 10 different signals you need to write in this always block. So in that case, a better way to write is that always at the rate of star. It means that whatever is being read inside this always block, or the always block becomes sensitive to all of them, right? And if you are trying to model combinational circuit, it is better to write always at star rather than naming all the signals, because you may miss some signal. If you miss some signal, what can be the problem? Any answer? Suppose you write always at and A, B, and there were a list of signal on which your always block should be triggered, and you miss some signal, and you while modeling, what will happen? Any guess? So in this case, what will happen is that your synthesis and simulation results will mismatch. Your synthesis doesn't look into the sensitivity list to decide your circuit, right? While simulation looks into your sensitivity list to understand that when to execute a code and produce the output, right? So if you write always always and miss some signal and miss some signal, then simulation will not trigger that block under that missing signal, and as a result of that, simulation will produce some different result and synthesis will produce different result, and as a result of that your design can fail. Why? Because you did simulation, you verified that the functionality is correct, but your simulation result was not as expected as per your circuit, and that's why your verification is failing and your circuit can fail, right? And therefore when you want to model a combinational circuit and you want to model it is always better to use use the syntax of always at star, always at star, ampersand star. Okay, so any questions? So now well, what will be the following modules synthesized to? Okay, so I'm giving you 2 modules. Okay, and just tell me the answer that what will be the output of this, each of these modules. Any answer?
The first one is D flip flops.
Okay, And in the second one, so how many flip-flops will be there in this case?
So 4.
Here you will have 4. In this case, see the difference is in the blocking and non-blocking.
Yes,
Okay,
sir.
here you have non-blocking, here you have blocking. That is the only difference in these two blocks. In the second one, how many will be there?
Sir, only one, sir, I think.
In second, you will have only one. Any other participants want to comment on this?
Sir, first one would be a shift register, maybe.
So here you will have 4, right? 4
Yes, a
flip-flops.
serial in, serial out.
Okay. And in this case? And in the
Parallel in,
second,
parallel out.
there is only one input, right? In one. How can it be parallel in, parallel out?
Sorry. Serial in and the parallel out.
There is only one output. How can it be parallel out? See, output is only out one, right? How can it be parallel out? Here also you have only one in, one out, right? And the clock. That are the only out. So you have to think that how this will be executed in the blocking assignment, and how this one will be executed. This is non-blocking assignment, right? So actually what will happen that this will give you only one flip-flop and this one will give you 4 flip-flop. This will be a shift register kind of thing. Okay. Now why it will happen like that, let me explain. Okay. So this is a very important concept, that this blocking and non-blocking assignment, if you don't understand, if you understand this, then many things will become actually easy in simulation and synthesis. So in this case, these statements will be executed similar as your blocking assignment is nothing but your as you do in your normal programming language. This first statement will go, then the next statement, third, and so on, right? So in this case, what will happen? That whatever is in, it will go to res1. Then the next statement, whatever is res, you go to res2, right? So whatever in res2 goes to res3, and whatever is in res3 goes to out. And all these 4 statements gets executed at the same clock edge. Once a clock edge is there, right, all these operation happens together. In1 gets to res1, res1 gets to res2, res2 gets to res3, and res3 goes to out. So whenever the clock comes, what will be the value of out1? Any answer?
Sir, in one.
Right. So you will get an in1 whenever the clock is happening, right? So you will get a circuit something like this. Clock in1 and out1. You will have only one flip-flop, right? In this case. So because this is behaving like a normal programming language, this is a blocking assignment. So whatever you applied at the input, you will get at the output and out1 at the clock edge, every clock edge, right? Whenever clock is coming, so only one flip-flop will be inferred in this case. All these intermediate variable will be optimized out by the synthesis tool. You will get only one flip-flop. In the second case, what will happen? In the second case, it will happen is that in1 is getting the value of res1 is getting the value of in1, right? Now res1 is not yet updated. Res1 is not yet updated. The next statement is getting executed, right? It is non-block. Now whatever the old value of res1 was there, that is going to res2, right? So res2 is getting the old value of res1, And again, rest 2 is not yet updated. The statement goes, execution goes to the next statement. And then rest 3 gets the value of old value of rest 2. Why? Because rest 2 is not yet updated. The LHS is not yet not executed. Only RHS is being executed, right? So rest 3 will get the old value of rest 2. And similarly, rest 3 will get an old value of rest 2, and out 1 will get the old value of rest 3, right? And therefore, this one will be a shift register, right? If you think of a shift register, it will be something like this, right? You have a clock. So whatever you give at in1, it will go to reg1. And whatever the old value of reg1, whenever clock will come, that will be captured to reg2, right? And whatever the old value of reg2 was, that in the same clock cycle, that goes to reg3. And whatever the old value of reg3 was, that will be captured in the same clock cycle to out. So this is how the shift register will be inferred. So as a thumb rule, what you should do is that whenever you want to implement or have a circuit in which you want to have a sequential circuit, here you want a sequential circuit, you should use non-blocking assignment for sequential circuit. And whenever you want to model a combinational circuit, it is better to use a blocking assignment. Okay, blocking assignment. Here you have non-blocking. Okay. Any question? Okay. So we'll be looking briefly at simulation, how it internally works, and also a synthesis. Let's take a break of 5 minutes, and we meet at let me see the time. It is 11:42. We'll meet at 11:47. Okay. So let's meet at 11 in 5 minutes. Okay, so let's restart. So any questions from what we have discussed so far? Can you hear me?
Yes, sir.
Okay, so let's move forward. Okay, so now we'll see that very briefly that how simulation works. Okay, so so there are two types of simulation. One is continuous simulation. Simulation is based on some formula using or there is some differential equation that needs to be solved. For example, if you do the simulation of circuit simulation using SPICE, or if you are simulating the trajectory of a rocket, then those are continuous simulation. You are doing based on your formula. You find some output for a given duration, right? Now, but in digital circuits, what simulation we do is it is a discrete or event driven simulation. So in event driven simulation, what happens is that when a signal on an input changes, it changes the output, and the output further changes the input and so on. So in event driven simulation, there is a chain of cause and effect, and as a result of that, the value of signal changes and you get the output at the end, right? So the simulation of design using Verilog is an example of event driven or discrete simulation. Okay, it is done at discrete points. Whenever there is a change in the cause, the effect has to be computed, right? So now what is the mechanism of event based simulation? So in Verilog, there are two types of elements in simulation. One is the block of RTL code, right? So you have the RTL code, and inside this you have a block, right? So this block constitutes one of the one of the types of elements in simulation. So evaluation is required if there is a change in the signal in the sensitivity list. So this is the sensitivity list. If the signal changes, right, either in one or in two changes, then this block or this begin end block will be executed. So this is one type of element that is used in simulation. Other type of element is a gate, right? So whenever you have a gate, and the evaluation is required whenever there is a change in input. So whenever there is A, B, C, or D is changing, then Z needs to be recomputed. So there are two types of elements in simulation: a block of RTL code or the gate, right? Now, now in event-based simulation, there is something known as event. Now, what is an event? Event is anything that requires simulator to take some action. For example, change in value of a net or variable. So the event is what a simulator event is said to happen when the simulator needs to take some action. Okay, so when, for example, a change in value of a net or variable, then the effect of that change needs to be computed, and therefore this is an event. Now, events are of two types in Verilog. One is the update event, and the other is as an evaluation event. So what is an update event? So in update event occurs when the value of a net or a variable in a circuit changes. For example, we say that when A changes, so if A changes, the value of an net or variable is changing, right? So A changes, that is an update event, right? So the other type of event is evaluation event, meaning that when an update event has occurred, then evaluation event is required at all the gates in the fan out of the net. So if you consider this circuit, then whenever an update event happened at this net, then all the net fan out of the all the gates in the fan out of this net. So in this fan out you have G1, right? So you will have you need to make an evaluation at G1. So all the gates in the fan out of a net needs to be evaluated, and evaluation event is set to occur at G1. And all the blocks statements that are sensitive to that event, that will be evaluated. For example, if you have this block of code A, B, C, D, so this always block is sensitive to A, B, C, A, B, or C, or D. Now, if A changes, then this evaluation needs to happen at 1, right? Because A is changing, right? So all the block statements that are sensitive to that event needs to be reevaluated. Okay, so what I'm describing this slide is not that what does a simulator internally does when it carries out the simulation, and why it is important, because if you understand that what internally simulator is doing, then you can easily predict results and also debug the cases. For example, you are expecting something to be in the output from an RTL code or test bench, but it is not producing that output. Now, how to debug? So to debug that, you should understand that what did the simulator do? How did it compute, right? Otherwise, you'll never be able to debug your design, your test benches, and other things. To debug and those things, you should understand that what the simulator will do. For example, if A is changing, why say Z2 is not changing? Suppose, right? So if you are debugging that, you should understand that when Z2 will expected to change, right? And so on. So you should understand that how this circuit will be simulated, and that will help you a lot in building the foundation for simulation. And that's why I'm discussing this. So there are two types of event. One is update event, the other is evaluation event. Now, how does the simulation progress? An evaluation event can lead to change the value of a net or variable, and in such cases, update events are generated for the affected net or variable. So if we take this circuit, we said that A change, there was an update. Suppose this is what we have written in our test bench, that D is equal to 0, A is rising from 0 to 1 after some time, and B is equal to 1, and C is equal to 0. We have written given this as a test vector in our test bench. Now, how the simulator will progress? So an update event will be created whenever A is changed, right? Now we saw that because of this update event, there will be an evaluation event in G1, or Y will change. So Y will be evaluated, right? Now evaluation event at G1 leads to a change in Y, because B is 1, A is becoming 1. So initially value was 0 and now it will become 1. So evaluation event at G1 leads to change in Y. Now Y is changing, and therefore an update event is created, right? So update of A created evaluation in G1, and evaluation in G1 created an update at Y, right? And now an update event can trigger further evaluation event. Now Y is changing, then what update events will be created? Now Y, because of the update event at Y, what evaluation events will be created? Any answer?
Sir, at G2 and G3 evaluation event.
Yeah, so two events will be evaluation events will be created. One at G2, other is G3, right? So now the update event is generated at Y0 to 1, leads to evaluation events at G2 and G3, or as a result of that, the Z1 and Z2 will be evaluated, and so on. So now because of this evaluation event at G2, what will happen? What update events will be created? When you evaluate G2, what update event will be created?
Z1.
Right, Z1, because the value of Z1 is changing from initially to 0 to 1. Now, when you do the evaluation of G3, what update event will be created?
Z2.
No, the answer is that there will be no evaluation event, update event created. Why? Because Z2 is already 0, because C was 0, and therefore G3 will not be actually, the evaluation of G3 will not create an update event. Why? Because the Z2 value is not changing. It is remaining 0. It was earlier also 0, now also 0, right? So the evaluation event here there will be no evaluation event. There will be no update event. There will be only update event on Z, right? And that is what you need to, suppose you wrote a test bench, now Z2 is not changing, right? Why it is not changing? The reason is C is held to 0, right? And to understand these all things, you need to understand what simulators do internally. Okay, so I will not go more into deep into simulation. I'll just explain a few more things that are important while debugging. One, the most important thing is the race condition in simulation, right? So what is a race condition? Now in Verilog, language specification defines which statements have a guaranteed order of execution and which statements have no guaranteed order of execution, right? For example, if the statements inside an always block, it will always be executed sequentially, right? One after the other. This is guaranteed. But if you have multiple always block, any one can be triggered first, right? Depending if the same event occurs, for example, clock here also, clock here also. Now, even if you write this block above this one, it is not guaranteed that this one will be triggered first. This one can also be triggered first, depending on the simulator, right? So that is not guaranteed. So those are that is not. So there are something which is guaranteed by the language. The something which is not guaranteed. When two or more statements that are scheduled to execute in the same simulation time and would give different results when the order of execution of statements are changed, then a race condition is set to occur. Okay, so what is the basic definition of a race condition? Race condition means that if you have a set of code, we have a Verilog code, you have if you change the order of execution of those code as permitted by IEEE standard, and the result will vary, then you said that there is a race condition is there in our code, and we should avoid that. Why? Because the different simulator will give you different result, and your verification is not correct in that case. Why? Because your verification result depends on a particular simulator that you are using. Your circuit may not be guaranteed to work the same way, because synthesis may be treating that same construct in a different way, and it will produce a circuit which is different than what you have actually simulated from. And therefore, race condition should be avoided. Okay, race condition can occur in many situations. Race conditions are difficult to debug. Some guidelines or good coding practice can be followed to avoid race condition. Now let me show you what is a race condition. Suppose you write this code, right? Now if in this code, if the first block is executed and then the second block, then the final result will be this: A is equal to 1 and B is equal to 0. But if the first block is executed, the second block is executed first, and then the first block, then the output, the final result will be A is equal to 0, B is equal to 1. And therefore, the output of these signals, or the value of this signal, depend on the order of execution of initial block, and therefore there is a race condition, and this is not a good code, right? This is not a good code or a good writing practice. So you should not write a code in which there are race conditions, right? So this is an example of a race condition. Okay. Now let's take another example. Okay, that was a very easy race condition. Now here, is there a race condition in any of this block? I give you 1 minute to look into it and give an answer. Do you have any answer? Okay, so let's see the first one. Okay, let's assume that initially the value of A was 0. Suppose initial value of A was 0, right? Now, suppose this code is executed, this always, so now you see that there are two always blocks, both are sensitive to clock. Okay, now these two blocks will be executed concurrently. Now simulator can choose either this one is executed first or this one be executed first. And if the results vary in the because of the order, then we say that there is a race condition. Now suppose this is the code, and suppose the first block is executed. Okay, then in that case, what will be the value of A? It will become A is equal to A plus 1, so A becomes 1, right? Initial, we are assuming A was initially 0, right? So now A becomes 1. Now what about B? Now B is equal to A plus 1 is equal, that will 2. B will become 2. This is if this order was there. Now suppose I reverse the order of always block, that is permitted by IEEE standard or the language, right? So any of these always block can be executed first, right, as per the standard. So now we execute this, right? So in this case, what will be the value of B? Because initial value of A was 0, it will become 1, right? And then A will become from 0 to 1, you will have 1. So you see that in now you have a value of B is equal to 1, but in the other case, you had a B value of B is equal to 2. So race condition is set to occur. Okay, so in this code, there is a race, right? Now, is the race there in the second one, in the second block, non-blocking state? So here we have used blocking statement. In the other one, we are using the everything else is same. Only instead of blocking, we are changing it to non-blocking. Will there be a race in the second block? Okay, so now let's do the same thing here. Now suppose the code or the execution is this first and then this one, right? And suppose initial value of 0, A was 0, right? So what will happen? In the first, what the RHS will be executed, right? So A is scheduled to be updated to 1, but the value of A, that is in the LHS, it is not yet changed, right? So the value of A will remain the same, right? It will be currently the value of A is still 0. Only A is scheduled to be updated to 1, right? And in the second case, and then the second, this is a non-blocking, so this will be executed. The next statement will be executed. Now B is scheduled to be updated to what value? Since current value of A is 0, it is scheduled to be updated the value of 1. B is scheduled to be updated a value of 1. Once all these LHS is updated, RHS are evaluated, and what needs to be assigned to LHS is decided, then the updation will happen. Now, suppose this one was updated first, then the value of A will change to 1, and the B value will change to 1, right? Because now the whatever is on the RHS, that is not evaluated again. It was already decided that I have to assign B to the value 1. So you'll get A is equal to 1, B is equal to 1. Now, if you change the order of execution, what will happen? Now A was initially 0, so B is scheduled to be assigned the value of 1, right? And similarly, A will be scheduled to be assigned a value of 1, right? A was 0, so A plus 1 is 1, right? And in the next pass, then B will be updated to 1 and A will be updated to 1, right? So you will get the answer as B is equal to 1, A is equal to 1. Either the always block is executed, either the first always block or the second always block is executed, will get the same answer, right? And therefore, there is no race condition in this, no race condition. No race condition here, and you have race condition here, right? And that's why I said that you should follow a thumb rule, that if I want to model a sequential circuit, it is a sequential circuit because you are modeling a flip-flop kind of thing. You have a possessed, you should use a non-blocking assignment. For sequential circuit, you should have non-blocking assignment. And for combinational circuit, you should use a blocking assignment. It is a safe, right? So this is what I meant by there are some rules which are or good coding practices by which race condition can be avoided. If you don't follow these rules, then there will be problem here. Okay, any questions? If you don't have any question, let me move to describing how synthesis works. Okay, we saw that how simulation works in the simulator very briefly, very top level view that simulation occurs by events, update event, then evaluation event, update event, evaluation event, and so on till the end of event, right? So where end of simulation time, this is done, and you get the result. Now let's look briefly at how does the synthesis work. Okay, very briefly. So in synthesis, you give an RTL, you give the library, you give the constraint, finally you get a netlist out of it, right? So now, when you give an RTL, what are the steps that is done inside this tool, right? When to get this netlist, and it is very important to understand, because many of the time you don't you need to debug that. Okay, I gave this circuit, now why did it produce my circuit this kind of or why did the logic synthesis tool give me this output, right? And now I could debug it. Probably instead of this kind of structure, I would have expected some other kind of structure. How can I manipulate the tool options to get whatever I want, right? To manipulate a tool, you need to understand what the tool is doing internally. Then only you will be able to manipulate those tools very effectively. And to become a good VLSI designer or ASIC designer, you should know the little bit about at least a little bit about the internal working of the synthesis tool. So these are the steps that are done internally. The RTL you take, then it is parsed, then analysis and elaboration is done, then technology independent circuit is created, then logic optimization is done, and technology mapping is done, and timing driven optimization is done. Now let me describe these steps very briefly, all of them one by one. Okay, so what is the parsing step? Okay, so in parsing, you have a file, you give a Verilog file, right? In a Verilog file, you have module and various kind of signals and so on. So the tool will first read your file. It will read the input RTL. It will break it into tokens, meaning that there is an input, there is a module keyword, there is an end module, then there is an input port, and so on. So it will read that the tokens of these are the keywords of the languages, these are identifiers, and so on. And the tool will internally build a data structure in which in the information of your the information of your RTL file is kept. And at this time, it will verify the grammar. For example, if you have given a module, whether you have given an end module or not. If you have not given an end module, then that is a kind of an error condition, right? And therefore, the tool will report you a syntax error, right? So if you have syntax error in your file, the tool will report the error at this point of time. Suppose it was that the tool was not having any syntax error, then it will build a parse tree and it will go to the next step, that is analysis and elaboration. Okay, now it will in the analysis and elaboration, it will make the connections. So when we are doing parsing, what it will do is that it will just create different modules. It will create modules, it will create ports internally in its data structure, but it will not say that suppose this module was instantiated in this another module, then the internal structural description or in the internal data structure, those connections are initially not built. But during elaboration, those connections are built. And suppose you instantiated a module whose reference you have not given, then it is a kind of probably you forgot to give an RTL file for that or something, and then it will create a black box kind of module for that, right? So those kind of thing is done in elaboration. That is, whatever references are used inside a module, those are checked. If it doesn't exist, then it will give you an information, either an error or a warning that this module is a black box. I didn't get a reference for this module, and so on. So that kind of thing is done. And there is something as parameters in Verilog, and those based on those parameters, new modules can be created. And also in this analysis and elaboration phase, there will be some compiler based optimization. That is that these kind of optimizations are same that is done by the compiler on your C code or C++ code. For example, constant folding, loop unrolling, and so on. So the constant folding means that suppose you have written A is equal to 2, and then you have written B is equal to a plus 5, right? So it implies that b is also a constant, right? It is the tool shouldn't use a adder for this. It can simply say that b is equal to 7, right? So this is what constant folding means. Similarly, common sub-expression removal. So if you are writing many times, say y is equal to a star b, z is equal to a star b plus c, then you write w is equal to m plus a star b star c, right? Now you see that a star b is common everywhere, right? So it can, instead of putting multiplier at all the places, the tool will say that, okay, this expression is common, remove it, and instead of that add another one. Say you create one variable I is equal to a star b, a star b is equal to I, and replace everywhere with I, right? Then there can be an optimization, for example, strength reduction. So in strength reduction, suppose you have written A is equal to B star 2, right? Now here you have used a multiplier, but multiplier is a costly resource. So instead of using a multiplier, the tool can say that, okay, it is multiplication just by 2. I can simply shift it, by towards left, right? Shift towards left by one position, and you will get a kind of multiplication by 2, right? So if you shift left, then you can get a multiplication by 2, and if you shift right, then we will be getting a division by 2, right? So those kind of, so rather than using a costly resource, use a simpler resources, right? That is what is strength reduction. Then there can be tree height reduction. For example, you wrote a expression a plus b plus c plus d, right? Z is equal to a plus. One way to implement is that you have one adder, right? And you have another adder. Then, okay, so let me draw a better diagram. It may become confusing. Okay, suppose you wrote an expression z is equal to a plus b plus c plus d, right? Now if you try to implement it, you can say that this is an adder a b, right? So whatever is coming, the output of it goes to c, and whatever the output goes to c plus d, and this is your z, right? Now if you do like this, then what will be the longest path of delay? It will be from here to here, right? And therefore the critical path delay, it will be much higher in this case, and you want to reduce the maximum delay in your circuit. So maximum delay is this one, in which you have 1, 2, 3 adders. Now rather than implementing like this, we want to reduce the height of a tree. If you look into it, it is kind of a binary tree, right? Now you can implement it in like this, right? You have plus here, yeah, plus here, and plus here. Here you say I take A, I take B, here you take C, you take D, right? So you add A plus B, whatever the result is, you get C plus D. So this is tree height reduction. Here the height was 1, 2, 3 adders. Now here you have two adders, 1, right? And therefore the height is reduced, and as a result of that, the delay from A to any of this path is much lesser. Here you had 3 adders, and here you will have 2 adders only, right? The number of adder is not changing. It is here also 3, here also 3, but the delay will decrease, right? So this is one of the optimizations that the tool will do. Then there will be a dead code removal. You have written some code like, say, z is equal to 0. Somehow it is evaluating to 0. And then there is a code, if 0, then do something. Or rather, if z, do something, right? So everything inside this code, if a part, that is a dead code, it will never be executed. So that can be removed and you need not implement that in your circuit. So the synthesis tool will internally do this optimization. After that, technology independent circuit is done or created after or by simple translation of logic of the RTL. You take the tool will take the RTL and corresponding to various constructs, it will create a net list or a crude net list in which not much optimization is done, and it is based on generalized gates. So it is not using the gates of the technology library at this point of time. Okay, so in this case, there can be resource sharing, unsharing, and many other kind of optimization that can be done at this RTL level, okay, or RTL synthesis level. So here you are basically translating your RTL code to the corresponding netlist. Then comes the phase of logic optimization. Okay, now logic optimization is technology independent. Till now, we have not used the technology library anywhere, the standard cells anywhere. We are doing technology independent logic of independent optimization of the circuit. So here now the tool will do many kinds of optimization. So the given a logic circuit, it will find an equivalent representation of the circuit that reduces a given cost and satisfies the given constraint. That is the basic problem for logic optimization, and it typically finds representation of a circuit with minimum area meeting the delay constraint. At this point in time, the area will be minimized, and the timing area estimates are based on just gate count and depth of the logic. It will be done, but we mostly do the area optimization at this point of time at logic optimization just after RTL synthesis. We have not used the technology library, so the timing of the circuit is not well cannot be computed accurately, and that's why we don't do a rigorous timing analysis and timing optimization of the circuit at this point of time. Or rather, I'm describing all these two steps that will be done by the tool while you do carry out the synthesis, right? So during synthesis, when it is doing logic optimization, first logic optimization is done without using your standard cells, your technology lab. Okay, so these kind of optimizations will do it will do two-level logic optimization or multi-level logic optimization. So these optimizations are similar to what you have done in your BTech courses. For example, you might have studied about Carnot map, right? So you have done optimization of say Carnot map of a function of say 3 variable or 4 variable, and maximum probably you might have gone up to 5 variable for using a Carnot map. But the problem that the synthesis tool encountered for industry standard design is that the number of variables will be range of hundreds. It will be say the number of variable can be 20, 30, 100, or even 200 or more. So so if the number of variables becomes too large, then the techniques that you have studied in your BTech courses, for example, Carnot map, those will fail, though you cannot apply those techniques. But you apply many other types of logic optimization. So these are known as two-level logic optimization based on some heuristics, or multi-level logic optimization based on transformations, and various passes are done, or some algorithm is there which is basically trying to reduce the area given an initial circuit, and that is done in the logic optimization phase. And after this logic optimization, now comes your technology library. Okay, so in this phase, the technology library that you have given, that will be used. Okay, and also your constraint file, the SDC file, .sdc file, that will be used. Till now, from here to here, all the tool required was your RTL, only your RTL. But after this technology mapping and timing device optimization and giving you final netlist, here you need your technology library and the attributes of the cell. Why it needs attribute of the cell? Because it needs to compute the area, delay, and so on. So to get those attributes, to get those attributes, you need to give the technology library and SDC file for doing the timing analysis. So technology mapping is what is done in technology mapping is that we bind generalized gates with gates specified in the technology library, and area and timing constraints are considered during mapping. Okay, so let me just give you an example of what or rather what problems are solved in technology mapping. So in technology mapping, it can do a minimum area or area minimization for a given delay, or it can minimize power for a given delay, or it can minimize the delay for a given area. So as a designer, you can give the various options to the technology mapper, that what level of effort does it need to make, whether it needs to optimize for area, optimize for timing, or various other attributes, right? So a designer has some control over this mapping algorithm, that how the mapper, the synthesis tool will do the mapping. Okay, now the attributes and why the technology library is required for doing this for technology mapping. It is because it needs technology mapping for knowing the area, delay, power of each of the cells. For example, if you have an inverter in your library and it want to instantiate that inverter in your design, then what is the area of this inverter? Whether it should use an inverter I1 or an I2, which one is better in terms of area, right? So though that information is present in your library, and from there it instantiates the appropriate cells in your design. Now, suppose this was this you gave this as a cell as an input, and suppose your library contained only two cells, a NAND gate and an inverter, and the cost of area is 1 and 2 in the other, right? Now, how will this will be mapped to these gates, right? So it will be mapped somehow like this. See, this is an AND gate, this is an OR gate, and this is an AND gate. We can think that there is an inverter here and also an inverter here. Here also you have inverter, and here also you have inverter, right? So if you have two inverter in series, the function remains the same, right? Now this inverter, if you add, this becomes the NAND gate, right? Now if what is an AND gate in which you have two inverters, right? Suppose you have A, B, right? And this is an OR gate. What will be this Z? This Z will be nothing but A bar plus B bar, right? So now if this is A bar plus B bar, and okay, and if you have an inverter here also, right? If you have an inverter, you put two inverters here, right? So if we take this one, then it is A bar plus B bar whole bar, which is nothing but A plus B, right? Sorry, A dot B. And if you take one more inverter, then suppose I have like this, right? So it is nothing but A bar. So let me describe it again. So this has, okay. Now, if I take this and bubbles, meaning that we are adding inverters, so this is becoming a NAND gate. This is becoming a NAND gate. Now, for this also we can this OR gate, right? You have inverter, and this is A, right? I can put and make this as a NOR gate and put an inverter. It is equivalent at this, right? This is A. So it is same as A bar plus B bar whole bar, right? This is this part, right? And then you take one more bar because of this inverter, right? Now, what is this? It is A bar. By De Morgan's law, we can say that A bar plus B bar, A bar plus B bar is nothing but, and whole bar is nothing but A dot B. And if we take this part, then it is. So again, this thing is nothing but a NAND gate, right? This is nothing but a NAND. So if we want to map this circuit to an inverter and an AND and a NAND gate, this will match to an inverter, this one to an inverter, this to an inverter, this will map to a NAND gate, these two will be mapped to NAND gate, and this is again nothing but a NAND gate, right? So what will be the total cost? The total cost will be 1 plus 1 plus 1, 3, right? And 1, 2, 3, 4, 4 for a NAND gate, and each has cost a cost of 2, right? So it will be 8 plus 3, that is 11, right? So 11 will be the total cost, right? And if in addition to this NAND gate and an inverter, we had an AND or invert gate, right? Suppose this AND or invert gate was there and its cost was 5, right? Then rather than putting NAND gate, it can implement this complete thing. This complete structure is nothing but 2 NAND gate followed by a NAND gate. Then it will implement using this standard cell, and the total cost will be 1, 1, 1. That is 3 for inverters, 1, 2 for this AND gate, sorry, NAND gate, and 5 for this gate, right? So the total cost will be 5 to 7, 3, 10, right? So if you have a richer set of library, then probably you can reduce the cost, and the technology mapping will look at all these options. Okay. Now, once you have got that done the technology mapping, then you have got netlist in terms of standard cells that are of the technology library, right? So technology mapping, what did it do? It converted all the cells which were of the generic nature to the cells which were present in the library, and also optimized area and other things while doing that. And after you have done the technology mapping, then you can compute the exact timing of your circuit, meaning your delay, the slack, and other things. And based on that, you can do timing optimization of the critical path. Okay, so that is done. The last step of that is the improvement of timing on the critical path, and internally it performs a static timing analysis. It can lead to some area increase, but it will improve that time. Okay, now so and whatever after these things, that the tool will give you the netlist, right? And this netlist can be used now in the physical design. So this is how very briefly I described that what the tool will internally do during the synthesis step. Okay, so I think that's the end for today. That's the last slide that I have. So that's the end of the today's lecture. If you have any question, I can take that. Do you have any questions? So what is static timing analysis? We'll look into that in the tomorrow's lecture. Yes.
Hello, sir.
Yes.
Sir, .stg file is always given by designer, or it can be generated using tools also.
See, tools, there are tools to generate SDC file, but the tool will give you a template. The tool cannot infer that what clock frequency you want to work with, right? So you have to fill all those data in your template. Okay, so at the end, you will have to manually change those SDC files. Okay, so typically SDC files are generated by human or created by human, right? If the tool generates, it will generate a template only. It cannot infer on its own that at what clock frequency you want your circuit to operate. Okay. Any other questions?
Yes, sir. Yes.
Okay, so if there are no questions, then that's the end of the class. Thank you very much.